Good morning, good afternoon, or good evening to you. My name is Arya Bhakta Adiatma with student number 90, 06, 30, 11, and 22. In this occasion, I want to convey about my work in finite elements analysis into the trusses with Openmodelica. Now, I'm gonna share screen my work. Okay, uh, this is the title that I mentioned before. Now, this is the problem that I chose, the problem number 4. We can see in this problem, there is 2D truss structure with cross-sectional area 10 centimeter square and modulus elasticity 200 gigapascal. Also, we can see the fixed support in point 3 and point 1 connection. So we can move to Openmodelica model. So the first, we must make the function file of stiffness matrix. We can input real A, real Y, and real X for matrix 4, 4 squared. And also we can define the float error and final constant real pi to multiply by Modelica math asin 1.0. We can move to algorithm. We can define the Y equals to A divided by 180 multiplied by pi, and we can define the x. This x matrix we can see in the book formula in the book. Uh, we can just type the cos and sine with Modelica Math, and we can move to I in 1 for loop and also in G and the stiffness matrix. Okay, we can move to other one. I don't forget to save it to for the run in the other step. So we can move to local global function. In this local global, we define the in the stiffness we can get the local of the stiffness, and this local global function we can uh, the global of multiply of the other local. So we can see the input is y for matrix square. We input the integer b, integer p1 and p2, and output real g b matrix. P1 and P2 P1 and P2 is to define the location or the x axial or y axial in this beam. We can move the algorithm for E in 1 to be a loop and G in 1 be a loop, also the same. And 4, we can now type the global for the every beam. We can see in the G, for example, G 2 multiplied by pi and 2 multiplied by P1, and the location or the matrix of Y22 square. Uh, we can use to another and n local global. So we can move to reaction force. This reaction force is to define the result of the reaction in trusses. We can input the integer n, input the real matrix A, input the real matrix B and C, and also X, and we can output real is solution and 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 last we can input define the real float error. So we can move the algorithm. We can see that x equals to a multiplied by b minus c into the I in one and loop. So n4. After that, get and the reaction traces. We move to Gauss-Jordan. In this Gauss-Jordan is to uh, give the solution of every reaction or deflection in these traces. We can see that input the integer n, real A in matrix, input will be in, output is x, and we also define the real fault error. We can move to algorithm. Also, in this, we use the Modelica matrix library to solve A and B. And for E in one and loop, and we get the if, we can add if and n goes Jordan. Finish. Don't forget to save it also. Now we hit for function that we have. We can move to the class file or class main file. This is the main file, the Trusses main. I name it Trusses main because this is the main file or master file. So we can now define the integer n equals to 8. This is we get from global matrix that there is 4 points connected. So we multiply that by 2. We define the real cross-section area in meter square also. So next is we define the modulus elasticity, the global matrix, the global initial matrix also, the solution of displacement, the global displacement. I mean, next is the xn, that we see that we can see the number, the global reaction force, and SOMAT and XMAT. Now we can next do boundary condition. We can see this B1 and B2, 1 and 3, that because in that trusses structure in point 3 and point 1 there is fixed connection. So the boundary connection is at point 1 and point 3. So we can move in analysis to the truss 1, truss 2, and FV truss. For the example, for truss 1, we can see the parameter real x1 equals 0 is the degree of the angle of the truss. Because the degree or the angle of the truss 1 is 0, we input the 0 number. Next is the small q1. Small q1 is defined to constant for the matrix. We can see the formula is the area multiplied by modulus elasticity defined by long of the beam. We can see the long of the beam truss 1 is 1 meter. So we can see the input is 1. So now we can define the real K1 matrix 4 square stiffness matrix, and we define integer P1A and P1B. And final is define the global trusses 1 with NN matrix. Also, the same step we use in the truss 2, 3, and 5, 4, and 5 with the variation in degrees and P location, PA and PB location. We can get the result. This is for trusses 3, 4, and 5. Now we can move to algorithm. The first is creating the global matrix. We can call the stiffness matrix file that we have do before, and we can call again the local global function that we have been make before, and don't forget to input the Q1 and P1A and P1B, or PA or PB. The same step we can use in K2, truss 2, 3, and 4, and 5. Now we can plus the G1, G2, G3, and G4, G5 to equal to G. And we can name the G as G initial. Now next to implementing boundary condition. For E in one end loop, Now uh, we can divide the boundary condition in global matrix. We can see this is the location of the uh, boundary condition in point 1 and point 3 in y-axis or x-axis. You can see the n4, and now we divide the matrix that uh, will 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 transform to one with Gauss Jordan. This is the the location of matrix that's in point one and the in point one connection and point three connection. Now, after we define that, we can solving this displacement by Gauss Jordan. We can call the function with input ng and x, so we can get the solution. Now we can solve the reaction force by also we can call the matrix and reaction trusses. We can name the reaction trusses as R with input and G initial, soulmate, and xmate. Now, after we finish that, we can end trusses main, so we can run this class. After we run, we can get this plotting. We can see that in reaction reaction plot, uh, there is uh, there is peak in point one in 1 second and back to zero, and again increase to the peak of 4 and 5 seconds. This is for reaction plotting. And next is the for deflection. We can see in point 3 or 3 seconds is in the peak of their deflection and back to the initial condition, and in the point 5 to 7 it's uh, decrease again to displacement. Okay, thank you for your attention. Good morning, good afternoon, or good evening. Goodbye. Thank you for attention.